Hello, welcome to Business Statistics. In this lecture, I will talk about Poisson distribution. So, a Poisson distribution is like a binomial distribution. So, if you see, a binomial distribution has success and failure. And we are interested in counting the successes or failures over a fixed number of repetitions. So what we do is we do the experiment again and again and count the number of successes and failure in a binomial distribution. So however, Poisson distribution it's similar to binomial distribution. However, we count the number of successes over a fixed amount of time or space. So we are using time and space to count the number of successes. So an example would be number of people arriving at an ATM in a given hour. Another example can be number of car accidents in a week. So if you see Poisson distribution, the success is not necessarily be a positive one. So like in this case, the car accidents is it's not a positive thing, but we call it as a success. So another example can be number of oil spills in a week or in a given year. So all these with respect to time, if we measure with respect to time, it follows it can be modeled as a Poisson distribution. So in order for any random variable to qualify for a Poisson distribution, we have two conditions. So the first condition would be success can occur one at a time. So that means two or more. Success at a time. So this is at time, so I'll erase it and rewrite it. So this cannot happen. So that means one success can happen at a given time. So what it means is, if you see our number of people arriving at a ATM, only one person can use an ATM counter. So that is one person can arrive at a time. Two or more people cannot use a single ATM counter. So the second condition would be the occurrence of success in any time period is independent of occurrence in any other time period. So what this means is, if you see our ATM example, the occurrence of success happening in any one time period is independent of occurrence in any other time period. So if we have 8 a.m. to 9 a.m., the number of people coming during that time period is independent of the number of people coming from 9:01 to 10 a.m. and then if we have 10:01 to 11 a.m. so they are independent of one another. So the number of people coming at 8 a.m. to 9 a.m. does not impact the number of people coming from 9 a.m. to 10 a.m. So it's a logical condition. So if these two conditions, if we have these two conditions, then we can say the variable can be a Poisson random variable. So if we have a Poisson random variable, that means we will have a Poisson distribution function or a probability distribution function. So Poisson probability distribution function, the formula would be P of capital X is equal to small x is equal to e power minus lambda multiplied by lambda power small x divided by x factorial. So where e is 2.71828 and lambda is, so this is lambda, it's called lambda. So lambda is the mean number of success. So if you see, this is mean, means our mean in previously we discussed mean is represented by mu, so it's lambda. Now it is lambda. So one of the peculiar cases of Poisson distribution is your variance sigma square. So this is our variance. So I will write VAR is also lambda. So that means our mean and variance both are same, which is lambda in Poisson distribution. That means our standard deviation sigma would be square root of lambda. So that's the that's what Poisson probability distribution function is. This is the function, and the mean is given by lambda, variance is given by lambda, and then the standard deviation is given by square root of lambda. So now, as we know the concept of Poisson distribution function, we will try to solve a problem on this. So if we have a ATM counter and 20 people arrive per hour. And it has a Poisson pattern. The arrival rate of the people has a Poisson pattern. So that means we are saying it's following a Poisson distribution. So we are interested in knowing, the question would be, the first question will be probability no one will arrive. In a 15-minute interval. So the thing is, it's saying no one will arrive. We can use our probability distribution function where P of capital X. So that means no one will arrive means zero arrival. So that is P of X is equal to 0. So firstly I will try to write the formula rather than directly going into the values. So our formula was P of X small x is equal to e power minus lambda power x divided by factorial x. So that means our x here, since we have no people arrive, would be 0. That means 0 arrival. So we can substitute all x as 0 and we know E is equal to 2.71828. So now we need lambda. So we need lambda. So if our problem, instead of 15 minutes, they would have said 1 hour, then our lambda would have directly been 20 people per hour. So our lambda would have been 20 people per hour. That is for 1 hour case. But since they are asking us 15 minutes, our lambda will change. So in 1 hour we have 20 people so we are asking ourselves in 15 minutes how many people will show up. So if you see, this is, I can say instead of 1 hour I will say it's in 60 minutes. So I'll just strike the 1 hour out. So that means in 15 minutes, if 60 people, 60 minutes, 20 people arrive, 15 minutes, how many people will arrive? We can do 15 multiplied by 20 divided by 60. So this is going to give us, this is 3, so this is going to give us 5. So 5 people will arrive every 15 minutes. So our new lambda would be, maybe I will write in a different column, would be 5 people for every 15 minutes. So now I can substitute the values. So this is P is equal to probability of capital X is equal to 0 e power minus lambda e power minus 5 power 0 divided by 0 factorial. So as you know, 5 power 0 is, this is 1, and then 0 factorial is 1, so I will be left with e power that is e is 2.71828 power negative 5. So if you calculate this, you will get 0.006738. So this is how we calculate. There is another way how you can calculate this. You know, x is equal to, our small x is equal to 0, and our lambda is 5. So we have a Poisson distribution table. So this is probability, so I will go to the table. This is a probability distribution function table. So if you see, we have lambda here, so that means the values 0.02, 0.03, 0.04, 0.05, those, that row is lambda values, and x values are columns like this 0, 0 or 1 or 2, so those are x values. So we are looking for a lambda of 5, so our lambda, I can go down and look for lambda of 5. So all the bold ones are across the row are lambda values. So this is lambda, which is 5. So now we are looking for 0 value, so this is 0. So that value, the value which we will get is 0.0067. So it's the same as that we got here. So we got 0.006738. So that's how you can use the table. So now if someone asks you what would be the probability that 4 customers will arrive, so that means px is equal to 4. So we will directly use the table. So we have x is equal to 4, lambda is equal to 5. So I will go to the table. So I have lambda is equal to 5 here. So I will go to, I am looking for 4, x is equal to 4, that is that row, this row. So the value would be 0.1755. So if we go back, this will be 0.1755. So now if someone asks us what is the probability that at least three people will arrive in a given hour. So that means we are looking for a probability p x greater than or equal to for a given hour. So as you know that a Poisson distribution, we don't have an upper limit. It keeps on increasing. However, the probability will decrease, right? So if it keeps on increasing, then greater than 3 means p of x is equal to 3 plus p of x is equal to 4, so on until if we have k events, p of x is equal to k. So it's very difficult to calculate until k, so since we don't know what is k. So one of the ways how we kind of maneuver this is we know the law of probability says p of x is equal to 0 plus p of x is equal to 1 plus p of x is equal to 2 plus p of x is equal to 3 plus p of x is equal to 4 plus so on until p of x is equal to k is equal to 1. So since we know this, now if you see this part, I wanted this part. So what I can do is to get that part, I can this is 2, I'm sorry, let me erase this. So we are looking for a value from p of x is equal to 3 to p of x is equal to k. So one of the ways what we can do is we can take this value to the other side. So what that means is p of x is equal to 3 plus p of x is equal to 4 plus so on, p of x is equal to k should be equal to 1 minus p of x is equal to 0 plus p of x is equal to 1 plus p of x is equal to 2. So we see this is 1 minus p of x is equal to 0. We can go to our table and see what is that value. So we have lambda 5 and x is equal to 0. So that value would be our 0.0067. So this value would be 0.0067 plus we can again go and look for p of x is equal to 1, which is 0.0337. So this would be 0.0337 plus p of x is equal to 2 is 0.0842. So we will 0.0842 so if we calculate it we will get 1 minus 0.1246, that is equal to 0.8754. So this concludes our lecture on Poisson distribution. Thank you.